Welcome to our channel. Let's begin the journey.
Today, we're taking a journey from the brilliant, eternal fire of living stars straight into the terrifying, absolute darkness of their violent deaths. You know, we look up at the night sky and see this peaceful, twinkling canvas. But the reality? The reality is far more dynamic and, honestly, a lot more dangerous. We're going to examine the life cycle of these cosmic giants, and we'll be focusing really closely on a startling prediction made by a man whose name is usually associated with a very earthly kind of destruction, J. Robert Oppenheimer. For literally thousands of years, humans just looked up and wondered what kind of fire could possibly burn so consistently out there in the freezing cold of space. But as we slowly began to understand their blazing lives, a much darker, far more unsettling question was just sort of waiting in the shadows. What exactly happens when they finally run out of fuel? Well, we are going to explore this catastrophic mystery, a reality that was pieced together by a series of extraordinary minds and ultimately envisioned in its final, terrifying form by Oppenheimer. Section 1. The Engine of Stars. Okay, to understand a star's death, we first have to look at its roaring life. It's like this colossal cosmic puzzle that was actually solved by the theoretical physicist Hans Bethe back in the early 20th century. Previously, scientists thought stars shined due to gravitational contraction. But if that were true, they'd only last a few tens of millions of years, and that's an absurdly small number compared to the already established billion-year age of our own Earth. So Bethe massively applied quantum mechanics to prove that deep within the dense, highly pressurized core of a star, hydrogen nuclei are constantly colliding and fusing into helium. Basically, every star is a giant nuclear reactor diligently forging elements, and this fusion releases enormous energy that perfectly matches Einstein's famous mass-energy equation. Section 2. Curving the cosmic fabric. So before we can fully grasp the devastating consequences of what happens when that massive nuclear engine shuts down, we've got to establish the foundational physical rules of the universe, courtesy of Albert Einstein. Einstein completely tore away the enduring veil of mystery around gravity. Before him, gravity was thought of as just some mystical, invisible pull operating instantly across empty space. But Einstein spent a grueling decade wrestling with these incredibly complex geometrical equations to show us that space and time are actually unified into a single, flexible, four-dimensional fabric known as spacetime. Think of it like placing a heavy bowling ball right in the middle of a trampoline. Extremely massive objects, like our sun or a giant star, create deep, sloping dents in this flexible cosmic fabric. The physicist John Wheeler elegantly summarized Einstein's core operating system of modern cosmology with this famous quote, "Matter tells spacetime how to curve, and spacetime tells matter how to move." It perfectly proves that gravity isn't some invisible tether. It's simply the physical curvature of the universe itself. Planets are just sliding gracefully along the invisible curves of the denses made by massive stars. And understanding this is the absolute foundation we need to figure out star death. Section 3. The mathematical boundaries. Right, so just months after Einstein published those overwhelmingly complex equations, an exact mathematical solution was found in the most unlikely of places. Amidst the filthy, violently artillery-battered trenches of World War I, a highly dedicated German physicist named Karl Schwarzschild made a chilling discovery. He took Einstein's math, precisely described the curvature of space-time around a spherical mass, and found an extreme consequence. He realized that if you were to compress a celestial body into a small enough physical radius, space-time bends so drastically that it entirely and inescapably closes in on itself. This creates an invisible boundary where the required escape velocity becomes vastly greater than the speed of light itself. Tragically, Schwarzschild died of illness at the front shortly after, never even knowing he had laid the mathematical foundation for black holes. Section 4. The ultimate weight limit. Then, fast forward to 1930. Picture a brilliant 19-year-old kid named Subramanian Chandrasekhar, sailing from India to England. On this humble ship journey, with just a scratch pad and some really complex equations, he found a deadly mathematical limit that acts as the definitive boundary dictating a star's fate. At the time, scientists firmly believed every single dying star would just gently cool down into a highly dense white dwarf. But Chandrasekhar proved that a white dwarf's stability actually relies on a delicate quantum phenomenon called electron degeneracy pressure. Basically, that's microscopic particles fundamentally refusing to be squeezed any closer together. His math definitively proved that if a dead star's mass exceeds 1.4 times the mass of our sun, that microscopic pressure entirely and utterly fails against the crushing force of gravity. So the universe had established an immutable cosmic rule. A dead star simply cannot remain a stable white dwarf if it's too heavy. If it crosses that 1.4 solar mass threshold, it must inevitably collapse into much more bizarre and devastating forms of matter. Now, the conservative scientists of his era fiercely opposed this idea. But the math? The math was undeniable.
Section 5, when the fuel runs out.
And this brings us directly to J. Robert Oppenheimer. Long before he ever stepped foot into the secretive Manhattan Project to become the father of the atomic bomb, Oppenheimer directed his formidable, visionary intellect at the violent deaths of these massive stars. While everyone else was focusing on how stars maintain their bright stability, Oppenheimer dared to ask a much darker question. When Hans Bathe's nuclear fusion engine finally shuts down, and Chandrasekhar's 1.4 mass limit is utterly shattered by a supermassive star, what is the ultimate victory of crushing gravity actually going to look like?
Well, let's walk through it. Oppenheimer and his colleagues realized that when a massive enough star dies, absolutely no natural force in existence will be strong enough to resist its own collapsing gravity. First, the nuclear fuel entirely exhausts. Then, colossal gravity endlessly crushes the remaining matter inward. The core just keeps shrinking continuously. It compresses down to an infinite density, crushing inward so intensely that conceptually it literally pierces the very fabric of space-time itself.
Section 6, piercing through space-time. Oppenheimer vividly described a theoretical process so radically extreme that it was initially largely ignored by many of his contemporary scientists. I mean, it just seemed entirely too wild to be real. But through his incredibly complex calculations, Oppenheimer formalized the concept of continuous gravitational collapse. He essentially proved, to the absolute awe of modern physics, that a dying star can literally tear a hole in the universe. It creates a region where gravity is so overwhelmingly dominant that it outright forbids everything from escaping. Not even the fastest thing in the universe, light, can get out. These visionary papers laid the very first foundational bricks for humanity's modern understanding of black holes. It's absolutely beautiful how this stepping stone logic compounded over the decades, isn't it? You have Schwarzschild finding the mathematical boundary during World War I. You have Arthur Eddington in 1919 traveling all the way to West Africa during an eclipse to empirically prove that massive objects physically bend ancient starlight, validating Einstein. Then Chandrasekhar finds the exact weight limit where quantum pressure fails. And finally, utilizing the math of all these peers, Oppenheimer was able to synthesize the ultimate monster lurking in the equations.
Section 7, the unseen gravitational monsters.
So what should you really take away from this explainer? It's the astonishing power of theoretical physics. Armed with just a brilliant imagination and a simple scratch pad, Oppenheimer stood on the shoulders of giants. By combining cosmic alchemy, the flexible fabric of space-time, and the realization that unyielding gravity eventually overpowers absolutely all known physical forces, he decoded a space-time rupture. He fundamentally reshaped our understanding of reality by proving that the universe allows massive stars to violently collapse into themselves, and he did it long before human instruments or telescopes could ever hope to actually see them.
And that leaves us right here, staring directly into the abyss. It's an incredibly humbling realization. We know the math, we understand the tremendous collapse of the star, and we know for sure that these regions aggressively swallow light entirely. But it leaves us to endlessly wonder, what unimaginable, chaotic rules actually operate deep within the monstrous darkness of a black hole? Keep that question in mind next time you look up at the stars tonight. Thank you so much for joining me.
The view from here is breathtaking. Command, we are in position and ready for the next phase. If you liked the video, subscribe and comment the topic you want next. Thanks for watching, and stay unstoppable.